Good morning, everyone. Welcome back. I'm a runaway academic. I'm now working in the fashion industry. Maybe you can't tell, but and I'm presenting a piece of work that we have been doing around product data, and arguably this is some kind of foundational capability that a business needs to have in order to understand its own customers, because the strongest signal is between customers and products and the way customers interact with products. So by better profiling our own products, we can better serve our customers. And we are a team of data scientists. So a couple of my colleagues are here today. You can talk about recommender systems with Matteo and about supply chain optimization with Martin. But without further ado, let's start. So this is a session about computer vision, but you'll see the computing vision side of this work is pretty basic. So I want to lower your expectations. It's around, as I said, classifying products in our catalog. A little bit about the company first, then I will give you the motivation for this work and talk about more into details about the approach and some preliminary results. So about the company, I guess you know ASOS in the UK, but I will start with the why. People buy what you do, people buy why you do it, not what you do. So our purpose is to give you the confidence of be whatever you want to be. Now, would you like to buy some clothes? So actually, the product is fashion and beauty for a target audience of 20-something. The company itself is relatively young, but it has been growing steadily, and it has now 16 million active customers, all online. And 70% of the traffic is from mobile devices. As a proposition, we have large number of styles which are on stock at any time. So around 85,000 different unique products that you can find on the catalog. And you can see where I'm going. So this is something that already presents a challenge in terms of the size of the catalog. This is the piece of work that I want to present today. So imagine that, first of all, as a way to scope the problem, I'm not talking about product-facing attributes. So not anything that you find already on the website, not the product type, not the color, not the size. So those attributes are always consistent and are always available for the customer. I'm talking about other attributes that are produced and consumed within the company by different divisions. So for instance, the buyers or the merchandisers, they might have attributes that relate to the specific style or design pattern, or attributes that relate to the kind of customer that a product is thought for. For example, when you have to create content, you need to have some kind of ideal customer in mind, and that's a product attribute. And as you can imagine, those attributes are mostly missing and also not always consistent. So there is a taxonomy that evolves over time, and the fact that we don't always have them doesn't allow us to use them for analytics, for forecasting. For example, we cannot say how many floral dresses we sell. precisely because the design pattern is not always there. We cannot recommend floral glasses, and so on and so forth. So this is the motivation for this work, and we see it as a foundational capability, a core proposition, but is to be consumed internally. So the goal of this work is to consolidate the data that we already have. Please feel free to interrupt me at any time. Okay, so this is the motivation, and what kind of data do we have to assign those attributes? We have the product images that you can find on a product page, and also the text description. And as you notice, the text description is already very detailed and contains a lot of the fine-grained information that would be hard to extract from images alone. And the text actually is a very good source of information. And by text, I mean the product description and also the product title. Product title is already manually tuned by the visual merchandisers to help customers surface relevant products when they search for products. So those two are already very informative. And we also use some of the metadata that we always have, for example, the division, or the gender of a product, and the brand, and the product type. And using those inputs, we want to be able to assign all of the attributes that we deem relevant for a specific product type. So for instance, as I was mentioning, the design pattern, so in this case, plain, or other attributes related to the shape of a product, for example, the kind of neckline or the sleeve length, but also attributes which are not as straightforward, like the event or the use occasion or the customer segment. So how do we do this? We have images and text, so I'm going to briefly talk about what we do with images and what we do with text. For images, I was saying pretty basic. We use a convolutional neural network to extract generic image descriptors. In this sense, we use deep learning just for representation learning, for generating features. And we started off with a classical VGG16, and we take the bottleneck features and we do a global max pooling of those. I will not, if it's okay, I will assume that everyone knows how this works. The only thing that we do that I want to mention is that we do this as a pre-processing step. So into production, there is a pipeline that just generates visual features, and we store them for downstream applications. For instance, the product attribute predictions that I'm talking about, but also for other purposes, as, for example, a hybrid recommender system that we are working on. And essentially, this is what we do with images. Then, for text, is again something similar. So it's not as fancy anymore, but I initially thought it was surprising to use convolutional neural networks for text. Now is almost a given, but if you consider that an image is essentially a matrix, so you already have a numerical representation of an image internally, you can also view a sentence as a matrix. If you take the word embeddings for each word in a sentence, and you build a sequence, and this sequence looks like a matrix, and where you have all the embeddings for each word, one after the other, and at that point you can treat it as an image, as a single line where the embeddings values would be the colors of these points along the line. And then you can run a one-dimensional convolution along this line. And this is actually a clever way to take word orders into account, and because you have convolutional filters that span over multiple words, and you can learn features in an end-to-end way. This is way faster to train than a convolutional neural network, a very deep convolutional neural network on images, because this one is not deep at all. It's essentially just a convolution layer and max pooling and a dense layer. But it's very effective. It beats a sparse representation of text, the classical TF-IDF plus linear model. And this is also something that is always good to check. You always need a baseline to make sure that you are doing something good. And we do this over the title and text description that you saw before. So this is it for text. And then we need to merge those two. But there are other issues that I haven't mentioned yet. So if you think about all the attributes that I was showing before, and the first slide, well, yeah, for example, so each attribute is itself a multi-class problem. So for example, the design pattern can be one of several. And those classes are themselves imbalanced. So for example, we have way more floral dresses than some other kind of dresses. And this is one possibly challenging fact. And another fact that you can observe here is that attributes are missing in different places. So different products might have labels that are present or not in this kind of way. So very few products will have all the labels. So if you wanted to go and use this data as your training set, it would be extremely, extremely small. And this is the same reason why we can't actually use this data as it is. Because if you have a model that requires all those labels at a time, you don't have enough data to train the model. And the same goes for our model. So this is another issue. Which is the third one there. So the training set is only partially annotated. And depending on the attribute, I might have more labels or less labels. And those labels are not always matching. And the other issue that we have is that those labels are actually not mutually independent. So for example, going back to the dress examples, it might be the case that floral dresses are more frequently seen on girly girl style products. And I don't know if that's correct, it's just an example. But just to see that if we were to just do a, a massive sigmoid binary cross entropy at the end, we wouldn't be able to take into account the fact that there might be interactions between those labels. And also there is some kind of hierarchy whereby, as I was saying, each attribute is in itself a multi-class problem. So how do we deal with this? There are very cool models in the state of the art. For example, it was mentioned before, dense captioning, where you have a classification network and a recurrent neural network, and you can, from an image, produce all the all the attributes in the caption. But with so many missing labels, it would be kind of hard to implement. You would have to have masking layers, and so we went for a much simpler approach that we took from a work on drug discovery, and we went for a multitask architecture. where we essentially have, I'm going to start from the bottom. We have one output per each attribute, and we use softmax in this case, because in this case we don't have thousands of classes for each attribute. Is around, I don't know, for example, for the design pattern, 22 classes, and we know that it's going to be one out of those 20-something classes, and we can have different layers, different output layers for different attributes, and this will take care of the fact that those are multi-class, and also we can weight the loss function differently for different attributes depending on the class frequencies to help with the fact that we have imbalanced problems. And so it looks like we have many models if we just look at the attribute output, but in reality, that's the only task-specific layer, the output layer. All the rest is shared, and we do hard parameter sharing. So each time that we update the model for one of the attributes, we are learning for all of them at the same time. And the model itself is pretty straightforward. So for images, we concatenate the embeddings that come out from the convolutional neural network, and we, together with the product type. For the text, we do the one-dimensional convolution end-to-end, as I was describing before. And for brand and gender division, we just do embeddings, learned end-to-end. And there is one thing that is interesting. To train this, we had to resort to some kind of custom procedure. So we do mini batches in a randomized order, one for each task. So we update the model one task at a time. And we have to use a simple SGD with even no momentum, because we found out that more refined optimizers like Adam or anything with adaptive gradient and momentum was kind of making the training unstable. And for example, some preliminary results, because we are still putting this into production, on a set of 33 attributes with 511 classes, we get an average F1 of 85%. And you can see that the model is able to learn attributes that are not just directly in the text or from the image. For example, the occasion of a product. So when you can use a product, you see the easiest one is wedding. So wedding clothing is really easy to spot, but there are some which are really tricky. For example, the difference between a going out bar dress and a going out club dress, I wouldn't be able to tell it, honestly. So these are indications that it's working. And another interesting thing is that we have a multi-modal model where we have both images and text as inputs. And what we see is that text is way more relevant than the images. This might have to do with the fact that the way we treat images is quite basic, yes, but also with the fact that you have so many fine-grained attributes which are explicitly stated oftentimes in the description. And just using images would make it very hard here to get to a decent classification. So to wrap up, we are working on this because we see it as a core capability. We want to be able to consolidate our own product data in order to allow for forecasting and better recommendations, more in-depth analytics, and so on. We use deep learning to leverage unstructured data, so images, text description, to produce structured data, an attribute table that anyone can use. And The approach we took is a multitask approach where we have one output per target. And this is good because we can have several data sets, essentially a data set per attribute, and it doesn't matter that they don't match in terms of the gaps. And it can exploit labels interactions because we have this shared body of the network. And it allows for an implicit data augmentation because, as I was saying, we can learn even for attributes that have very few annotations because when we fit for the other attributes, we also update the shared part of the model. And is a way to regularize because you are forcing the model to learn a representation that generalizes to multiple targets. And this acts as some kind of regularization. It makes it harder to overfit on a specific attribute. But it's slow to train, of course, and it's a bit tricky to train. So you have to be careful with the settings of your optimizer. Thank you so much.
Thank you very much.